In our everyday physical world, distance is a given. You can pull out a ruler and measure the exact space between two objects. But in the realm of pure mathematics, there is a place where distance, as we know it, simply doesn't exist. This is a topological space, a fluid, shape-shifting environment where objects can stretch and bend infinitely, and rigid grids are entirely useless. To navigate this wilderness, generations of students have relied on a single guide, James Munkres' textbook, Topology. As Munkres lays out right at the beginning, a topological space is remarkably barebones. It is just a set of points and a collection of subsets called a topology. There is no built-in ruler, no coordinates. Look at these simple bubbles grouping elements together. They define which points are near each other, what mathematicians call open sets. This gives us immense flexibility to study continuous transformations, but it leaves us completely blind if we actually need to calculate a precise distance. This creates a massive hurdle. If we want to use the tools of calculus, we need a metric, a strict mathematical ruler. Determining if and how a highly abstract space can be assigned one of these rulers is known as the metrizability problem. And we can't just assume a metric will work anywhere. Munkres explicitly warns that without strict conditions, topology is full of weird counterexamples that behave unpredictably, like the minimal, uncountable, well-ordered set, a space that actively defies standard numerical measurement. To build a bridge out of pure abstraction and back to concrete measurement, we have to tame the space. We must impose strict escalating rules on exactly how open sets and boundaries are allowed to interact. To prevent topological chaos, we use a collection of rules called the separation axioms. The most common starting point is the Hausdorff condition. The rule is intuitive. In a Hausdorff space, if you have two distinct points, you can always draw distinct, non-overlapping boundaries around each of them. They can be perfectly isolated in their own separate open sets. Isolating individual points stops the space from collapsing in on itself. But points are tiny. To guarantee that an entire complex space can be measured with a metric, the Hausdorff condition is simply too weak. We need a much stricter upgrade. We need what mathematicians call a normal space. Instead of just separating independent points, a normal space requires that you can take entire complex closed sets, like these two distinct shapes, and draw completely non-overlapping open boundaries around both of them. Proving a space meets this normal condition is a critical threshold. It provides the structural requirements we need before we can even attempt to apply a universal ruler. Securing that structural integrity is difficult. Many spaces that seem reasonable at first glance completely fail the normal test. Take the lower limit topology, for instance. It's built on the standard real number line, just with a slightly tweaked definition of an interval. Under the hood, its geometry is fractured, and it breaks when tested for normalcy. A moment of wonder. But for the spaces that do survive the test, Munkres introduces the center of Chapter 4, Urysohn's Lemma. This theorem provides the specific machinery to convert these abstract separation rules into real-world values. Here is exactly how the lemma works. In a normal space, you can always build a continuous function to bridge two separated closed sets. It takes one entire closed set and cleanly maps it to the value of 0. It maps the other set to 1, and between them it generates a perfectly smooth continuous gradient. This result is a direct translation. A universe that previously only understood abstract, shapeless groupings can now produce hard numerical values. Once you have the ability to generate these continuous functions, you have the ingredients needed to construct a universal metric, which leads directly to the resolution of our initial problem, the Urysohn metrization theorem. It proves that if a space is normal and has a countable basis, it can absolutely be measured with a standard distance function. The bridge is now complete. The twisting, abstract geometric forms of topology are effectively pinned down, meaning they can finally be analyzed with the standard tools of limits and derivatives found in calculus. This is the structural logic of Munkres' textbook. You start with the most rudimentary collections of sets. You carefully layer on the separation axioms, and eventually you build up to universal theorems of measurement. Mastering these precise logical stepping stones is the essence of higher mathematics. If you enjoyed this journey into the architecture of topology, hit the like button, subscribe to the channel, and let me know in the comments which mathematical deep dive we should tackle next.